All right. Hello, everybody. It's with great pleasure today that I announce today's distinguished lecture speaker, Dr. Bill Daly. EC is thrilled to have him over here today and join us. Before we get started, I wanted to share some exciting news that was just announced today by the Institute and by the college. The unveiling of Georgia Tech's AI Makerspace, which is a groundbreaking initiative in the collaboration with NVIDIA. This AI Makerspace, it expands on Georgia Tech's foundational theory-focused AI curriculum by offering students, particularly starting with undergraduate students, a very hands-on platform to tackle real-world, at-scale AI problems and develop advanced applications around it. So the first phase of this endeavor, just was announced today, is powered by 20 NVIDIA HGX H100 systems. And that'll, it's one of the most powerful computational resources that's out there, and it'll allow a lot of our undergraduate students to kind of experience that as a part of their curriculum and classroom teaching. So thanks a lot for the college and for all the other schools for the collaboration that we have had, and we have been planning for it with NVIDIA for many months, and finally it's great to see it come to fruition. So thank you, thanks to the college for their support. We are also extremely excited and thankful for NVIDIA's collaboration on this, and thank you, Bill, for joining us today and being a part of this general excitement around campus. Before I hand it off to him, I'd like to say a few words and the very important work and the impact he had on our field, in my field. So thank you, Bill, for coming here on campus today. Bill is a pioneering figure in computer engineering and science and system architecture. He joined NVIDIA in 2009 as the chief scientist. He brought a wealth of experience garnered from 12 years as the chair of the computer science department at Stanford. At Stanford, his team developed the system architecture, network architecture, signaling and routing and synchronization technology that's actually found in most of parallel computers today. His journey also includes groundbreaking work at institutions like MIT and Caltech, where he led the creation of experimental parallel computer systems that set new standards for synchronization and communication efficiency. His exceptional contributions to the field and to our professional society has earned him numerous accolades, including the membership to the National Academy of Engineering, fellowships in the American Academy of Arts and Sciences, IEEE and ACM, as well as extremely prestigious awards like the ACM Eckhart Mockley Award, the ACM Maurice Wilkes Award, and IEEE's Seymour Cray Award. I, of course, could go on and on. I have personally been impacted by many of the work that he has done as a grad student and beyond. So it's so super exciting to see him here today. But I want all of you to hear from him. So after the lecture, Professor Justin Romberg will join Bill for a short Q&A up front. And with that, I welcome you all to the lecture series. Thank you.
Well, thank you for that introduction. It's my real pleasure to be here, and I'm very excited about this AI makerspace you guys are doing. I think one of the big bottlenecks to AI is democratizing it. Right now, the resources to train big models are really in the hands of a few big corporations, and despite the fact that the government is trying to do this national AI resource in there, it's not really coming about for various reasons. And so it's great that Georgia Tech is moving ahead of that and doing it on its own. I think that's really going to make this a center of research and progress in AI. When I was on the plane yesterday putting together the slides for this talk, I decided to do what everybody does when they put together a talk. I would ask ChatGPT. So the first, it's all about getting the prompt right. So the first prompt is, give me an outline for a talk about directions in deep learning hardware. And I didn't like the answer to that. So then I asked, what would Bill Daly say about directions in deep learning hardware? And I got, well, it was not too bad an outline, but I decided to ignore it and do a different talk. A little while back, I was interviewed by the Wall Street Journal for an article about what it's taking to continue progress in computer design these days. And there's a period of time where process technology, especially true during the 90s, was improving fast enough that all you had to do was take your old design, redesign it with the new design rules, and it would basically go 50% faster and burn half the power, and you would be a hero, and then you could go spend a lot of time on the beach. But today, it's not so easy anymore. The process technology is giving us almost nothing. It's not absolutely nothing. We're in a transition now from 5 nanometer to 3 nanometer technology. We're probably getting about 10% in energy from that transition. Nothing in speed, nothing in cost. The transistors are actually more expensive per transistor at the 3 nanometer node than they are at the 5 nanometer node. And so all of the progress today in AI hardware and actually in computer hardware in general is coming down to, and to me this is a wonderful thing as a computer architect, is coming down to better computer architecture, better design. And it's out of cleverness. It's not out of getting a better process technology or a better transistor. It's about, given the transistors that we've had for decades, what clever things can you do with them? And the real problem we're trying to solve today is that of generative AI. And so I thought I would sort of put this chart up here, which is kind of the generative AI ecosystem. And everybody has pretty much the same model. I mean, there's not actually been a lot of innovation in models since the Attention is All You Need paper of 2017. Everybody's using transformers. There's a little bit of variation with people moving to mixture of experts. And this is really a way of economizing by not lighting up all the parameters with every query, but only the ones you need. The big expense is this training phase where these things called the chinchilla scaling laws that say if you have so many parameters, you need to train it on so many tokens. And that means as you get a bigger model, it doesn't just get linearly more expensive to train. It gets at least quadratically more expensive to train because you need to train it on more tokens as well. And today it's probably $10 to $50 million of GPU time to train a model from scratch, which is why very few people do that. Most people will start with a pre-trained model, one of the public domain ones like Llama 2 or so. But if you do want to train it from scratch, everything that's green here uses a lot of NVIDIA GPUs. That's coming from hardware vendors, and if you don't buy the hardware directly from us, from cloud service providers. So then you have a trained model, but to really use your generative AI for something useful, I always like to say that this trained model is our model with a bachelor's in liberal arts, right? It's got a general education. It's basically seen the entire contents of the web, right? That's basically what these training things are. We've had people scraping the web, and then they basically take the documents that are essentially photographs of documents. They do OCR on them so they can actually get the text out of those as well. But mostly it's basically pulling everything you can possibly find on the web and training your model. That's liberal arts education. We have a model at NVIDIA we call Chip Nemo that actually is greatly improving the productivity of our chip designers. And what we did is after getting a liberal arts model, and we actually just used Llama 2 for that, we took 48 billion tokens of our design documentation, RTL code, test code, various CAD scripts, and fed that in. And now when we have a junior designer, actually one of the biggest productivity gains, we have a junior designer and they want to know, how does this particular interface to the texture cache work? Rather than chewing up half an hour of a senior designer's time to get a tutorial on that, they can ask Chip Nemo, and Chip Nemo will give them a pretty good answer. It will also summarize bug reports. It will actually write RTL if you ask it, although that's not the major use of it. It'll write test scripts. It will write CAD scripts. If you want a particular analysis done, it will generate the right script to do that analysis. And this is the fine tuning of models. And most models to be useful, whether it's making designers more productive or in a business setting, are fine tuned for that setting. And then there's an additional stage where we use human feedback in this step called alignment to make the answers more amenable to what people are looking for. And that gives us a specialized model, whether it's for coding, medical advice, education, or so on. And then where most of the compute is going to happen in the future, as things mature, right now we're spending a lot of time training because we're still exploring, we're still trying to find out what the right models are. As things mature, most of the compute, probably 90%, will be on the inference side, where we basically have some query. And these days, we take that query, we run through the model once to generate a lookup in a database. We then pull all the relevant documents, stick them in the context window, and feed it through again to get the actual answer. And even though per word it's pretty cheap, it's millicents per word, the queries are going to be so prevalent. This is going to be what's really driving the economic engine. So let me tell you a little bit about how we got to this point and then where we're going from here. So deep learning is really enabled by hardware. The model, so there's three ingredients to a typical deep learning. There's the algorithms, which I've illustrated here by the AlexNet diagram. There's data, as I illustrated by the ImageNet data set, and then there's compute. The algorithms, the models have been around at least since the 1980s. deep neural networks, convolutional neural networks, training them with back propagation, stochastic gradient descent. I can point you to papers in the 1980s or earlier for all of those. The models were around. Big data sets like ImageNet and Pascal started coming around in the early 2000s. By 2005, we had very large labeled data sets of images, at least, and similar for speech and natural language. The missing ingredient, the spark, as it were, that ignited the fuel and air of data and model, was having enough compute to train a reasonable sized model in a reasonable amount of time. In this case, it was an NVIDIA Fermi generation GPU that trained AlexNet in about 2 weeks. And since then, it's really been an interesting rate of progress. The blue line here is sort of the rate of progress, and I should say rate of progress, rate of demand for computing. The demand for computing, which is in petaflops, not petaflops per second, but the absolute number of flops consumed, number of operations, went up about just a little bit under, it's more like 2.8x per year during the time of these convolutional networks doing image calculations. And then once transformers came out, in 2017, this rate of demand increased dramatically to 16 times per year. And this is because what people found is larger models trained on larger numbers of tokens give you better results, right? ChatGPT is more fun to talk with than BERT is. And as a result, in the hardware field, we feel tremendous pressure to provide this demand because we're limiting the rate of AI progress by the amount of compute that is available to train these models. So what have we done? Now let me just remind you of one number here, which is this is 10 to the 7th in 10 years. And actually, if you look at just that last little bit here, this is 6 years from 2018 to 2024, and that's like 10 to the 5th in 6 years. So it's more than an order of magnitude per year. So here's some history. So I got NVIDIA involved in deep learning. It started with a project actually back off the left edge of this thing. I had breakfast with my Stanford colleague, Andrew Ng, and he was telling me about work he was doing at Google finding cats on the internet. And while I was trying to figure out why anybody wanted to find cats on the internet, I did observe that he was doing it with 16,000 CPUs, and I figured we could do this with just a few GPUs. So I assigned a guy who worked in our research division to work with Andrew and port that code to GPUs. And so what he did with 16,000 CPUs, we did with 48 GPUs, and the code that came out of that became cuDNN. And so one of the reasons why NVIDIA is dominant in this field today is we had our first efforts at doing this stuff more than a decade ago, probably about 13 years ago in 2011. Now, at that point in time, the Kepler generation of GPUs was basically done. I mean, we still had a lot of physical design and verification and stuff to do, but we couldn't get any new features in there. So during the initial period on this chart, we were dealing with the GPUs that was really designed for graphics and scientific computing, and the major data type we had at hand was 32-bit floating point. And the biggest operation we had was a fuse multiply add. By the time we did our Maxwell and Pascal generations, which were really the same design, we knew enough that we wanted to do AI. We started putting specialized data types in. So we put in a 16-bit floating point, and we put in a dot product instruction, so we could do more operations with a single instruction. But it wasn't until Volta that we really kind of doubled down. We stuck with the FP16, but we added a matrix multiply instruction. I'll explain why that's important in a couple slides. So what our marketing people call tensor cores are really a set of instructions. The most common one is HMMA, half precision matrix multiply accumulate, that takes two 4x4 FP16 matrices, multiplies them together, and accumulates the result into an FP32 matrix. With that, we're now up to 125 ops, inference tops. With Pascal, with Turing, we introduced the Int8, the integer matrix multiply instruction. We put 2-to-1 sparsity into Ampere. With Hopper, we moved to FP16. And then Blackwell, which we just announced at the recent GTC, is 20,000 tops. And so this is not quite 5,000 at the top. It would be on the 4th floor on this chart. And basically, we're more than doubling performance every 2 years with each generation of technology, with very little of that coming from process technology. So let me break down where that performance improvement has come from over that period of time. And by far, and by the way, the red here I've added for Blackwell, even though all the details that aren't completely public at this point. The biggest gains are from number representation. And this is where you basically don't want to use more bits than you have to represent something, because it burns bandwidth to memory into registers, and arithmetic operations grow quadratically in cost with number of bits, right? Because if you think about doing a multiply, you're producing a partial product matrix that's the square of the number of bits. So going from FP32 to FP4 is not a gain of 8 in efficiency, it's a gain of 64 in efficiency. It really works out to more like 32x when you look at the actual energy numbers, because as you get smaller, you start getting limited by some of the constant factors on either side. So the biggest single thing is going from that FP32 to ultimately FP4 with Blackwell. The next biggest gain is adding complex instructions. This is why RISC is actually a bad idea. The whole idea of RISC is you should make instructions really simple so the compiler can assemble them any way you want. The problem is the overhead of fetching and decoding an instruction is, even for a GPU, which is a very simple pipeline, hundreds of times the cost of actually doing the instruction. So you really want to be doing hundreds of operations per instruction, amortize that cost out. And so by moving from single operations to dot product to matrix multiply, we basically get another 12.5x in improvement. The process hasn't been 0. It's probably been about 3x now that we're in a 4 nanometer technology. In Blackwell, we get a 2x from sparsity. We have increased our die size. And this is probably one of the biggest things that let Blackwell be 20,000 and not 10,000. It's really 2 GPUs, right? We have 2 reticle limited die that are connected together, so we can get twice as much performance. And while all this was going on the hardware side, by the way, the software people were pretty clever too, and probably got their own 1000x by coming up with more efficient models and techniques for tuning them. So let's talk a little bit about specialized instructions. So for a GPU, the overhead ratio is about, so call it 20 to 1. Well, this is a fuse multiply add, so it's 2 instructions. It's about 40 to 1. You spend about 40 times as much energy fetching the instruction, decoding it, fetching the operands, as an actual 32-bit multiplier add takes. So back when we were doing fuse multiply adds, our overhead was 2,000%. When we added the dot product instruction, we're now amortizing that same 30 picojoules of instruction fetch decode over 8 operations instead of 4. So now we only have a 5x overhead. By the time we get to HMMA and IMMA, it's now in the 15 to 20% overhead range. And what this means is that there's no gain in building a specialized accelerator. If you look at something like the Amazon Trainium or Inferium or the Google TPU, all of their energy is not going into matrix multiply either. They still have overhead of pulling stuff out of memories and sequencing things and all of that. And it actually is probably in the 15 to 20% or larger range. So at this point in time, we can be every bit as energy efficient and area efficient as a dedicated accelerator, but now we're in a completely programmable engine with a hugely evolved software ecosystem based on CUDA that lets us track new models more quickly, be very agile in doing the other parts of the code than the matrix multiply. So there's no advantage to building dedicated accelerators once you have large enough instructions. So what's in your cluster here, your AI makerspace, are Hopper H100s and H200s, which are essentially the same chip with slightly different memory systems. And the really important way to think about this is it's 4 petaflops of sparse FP8 and 900 gigabytes per second of memory bandwidth. What we announced at GTC, and it's working in our labs, although not shipping yet, is Blackwell. And a lot of what we did on Blackwell to get more performance is it's actually 2 GPUs. These are both reticle limited die, about 800 square millimeters, about 100 billion transistors each in TSMC4. The real innovation in my mind is what makes FP4 work, and I'll talk a little bit about that later. And it really has to do with being able to scale your numbers right, so that limited number of symbols you have to represent with FP4 hits in the right part of the number line to do the most good. We've bumped up both memory capacity and memory bandwidth considerably, and a new generation of NVLink. So this is really the starting point. But if you looked at that chart, even counting Blackwell with its additional sort of 4x on top of the 1,000, there's 4,000 gain in hardware there, and the demand went up by 10 to the 7th. So somehow there's like another 2,000 or so missing. And where that comes from is parallelism, right? So what I've talked about is the scaling of a single GPU. When we run these big training jobs, we exploit parallelism across several dimensions. First is each copy of the model, we break along pipeline stages, and then within each of those pipeline stages, we take the individual matrices and break them into submatrices. We call that tensor level parallelism. And so each plane of this image is basically running a separate model. And in the Hopper generation, it took 20 GPUs to hold a single, large, 1.8 teraparameter model. Today with Blackwell, it's more like 3 or 4 GPUs. And then in the other direction, the data parallel direction, we basically take copies of this model and we train them on different subsets of the data set. And basically they exchange parameters that they all update each epoch, a shared set of training parameters. And to do that with Blackwell, what we now offer is a single cabinet with 72 GPUs, 36 of our Grace CPUs, each of which has 72 ARM cores on it. And this basically is able to handle that model parallelism and data parallelism in a very tightly coupled way. Because this is all connected together with NVLink, it looks like one big GPU. With NVLink, you do loads and stores into the memory of the other GPUs within that NVLink domain. And the NVLink switch is actually, this whole middle section here is NVLink switches, has what's called sharp, which are collectives in the network. So we can do all reduce and maximum barrier and various collective operations that basically essentially double the performance of the network, because otherwise you would need 2 round trips through the network to do that reduction operation. We can do it with 1 round trip by doing the reduction in the network. And so the other sort of several thousand-fold needed to meet that demand has come by scaling out these things. This is 1 generation back of Hoppers, but it's the same thing where each of these racks contains, in this case, it's 5 8 GPU DGXs, so 40 GPUs. And the big training clusters these days that people at OpenAI and Microsoft and Google have are on the order of tens of thousands of GPUs. 30,000 is a typical number. And people are talking about building hundreds of thousands of GPUs to continue scaling the sizes of the models that they want.
What's the scale of that, the size of that?
Yes, these are quote 19-inch racks, which means they're really about 22 inches wide. So you figure about 2 feet for each of these, and there's, I think, 10 on each side. So this is about 40 feet long and maybe 3 feet deep. And people have large warehouse-sized buildings that they do with these. And so our story of this at NVIDIA is because we want to design not just the GPU chip, but the whole system. And to do that, we have to build and operate these systems ourselves. We understand how to do that. It turns out that building a system with 30,000 GPUs and having a significant amount of uptime on it is actually a non-trivial exercise in resilience and system management. So this sort of shows along along with my previous curve of scaling of demand, how our own NVIDIA operated data centers worked. We started with just a Pascal HGX in about 2015. That's just 8 GPUs. We built Saturn V, which is a half a petaflop in the Volta generation. And then with Amperes, we built Selene. And with Hopper, we built a system we call EOS, which is 43 exaflops of performance. The DOE makes a big deal about their exaflop machines. Those are 1 exaflop, but that is FP64, and this is FP8. But FP8 is what you want for AI in building machines like EOS. And there's a machine on the that's planned for Hopper that continues that scaling up there. Now, what really makes a difference, I think there are a lot of things that make a difference. If you look even at the Hopper generation of GPUs, everybody buys Hopper GPUs at their current gross margins, whatever they are, rather than an AMD GPU or one of the Intel or Qualcomm alternatives, because you can plug it in and get very high efficiency out of it. And part of that is, we've worked out how the FP8 works and the transformer engines and all that works very seamlessly. And what will happen is all of our competitors will look at that, and about 2 generations from now, that will appear in their hardware. And hopefully we will have clever enough ideas that we will be 2 generations ahead at that point in time. But the other thing that really differentiates it is, starting with that effort to find cats on the internet back in 2011, we have been working on software for AI, building up a bunch of things on top of CUDA with cuDNN and TensorRT and support for TensorFlow and PyTorch and actually half a dozen other frameworks, and then verticals on top of that, so that whatever application you have, it just works, and it works really efficiently. And the amount of performance improvement that comes from this software really can't be underestimated. One thing I like to point at is that just from software, in a typical interval between one generation of the ML-Perf benchmark and the next, our performance improvement is typically 2x or more. So this is the chart that we put out during the first ML-Perf benchmark with Hopper. And what we argued is a Hopper is 6.7 times faster than our previous benchmark, which was run on Ampere. Now, and that's on transformers like BERT here. But in fact, it was 6.7x faster than the previous benchmark on Ampere, but Ampere itself was 2.5 times faster. And that's because in that intervening, roughly 2-year period, we worked on the software on Ampere and improved its performance by that much. And so the mature software has real TCO advantages, and is something that is very difficult for a competitor to replicate. I like to look at the HPC wire stories that come out each time the ML-Perf benchmark comes out. The most recent one, this is just about a week ago, March 28th, when the ML-Perf 4.0 results came out. And I always like the headlines that say NVIDIA still dominates, because there are a lot of people out there trying to make a splash here. But back when I was a kid and people would talk about how fast their cars were, you would ultimately ask them to race for pink slips, and you would see whose car was really fast or whether they were willing to risk their car being that fast. You go back through the series of these, and the story is the same, that people don't really have the performance either in the hardware or the software stack that's tuned. They basically don't show up at ML-Perf. They'll run the benchmark themselves and decide it does them negative public relations good to post the actual facts. So that's the past and the present. Let's talk about where we're going. And a good way to figure out where we want to go is to look at where the energy goes. This is not in a GPU, actually. This is in our latest. We tend to prototype things in NVIDIA research by building AI accelerators. And this is in our latest AI accelerator that was published in the VLSI Circuits Conference. I think it was 2 years ago in 2022. And what you see is that still almost half the energy is in arithmetic. This is basically doing the math. And then much of the rest of it is moving the data around to do the math, both communication and reading and writing memories of various kinds. So this then says, how can we do that? Well, the first one is to do better number representation. If we can get by with fewer bits, that makes everything on this chart better, right? We move less data, the arithmetic gets cheaper. Another thing which is hard to really pull out of that chart is sparsity. My student Sung Hai and I kind of rediscovered this. It turns out, like most things, the original papers, in this case not the 1980s, but in the 1990s there were actually a bunch of papers about making neural networks sparse. We kind of rediscovered it in a NeurIPS paper in 2015. And what we found is you could take most models and lop 90% of the weights out of them with no loss of accuracy. We then have spent an enormous amount of time trying to figure out how to exploit that in hardware because it turns out if you make things irregular, which is what sparsity does, you burn so much energy figuring out which weights are non-zero and which ones are zero, that it more than offsets the gains by not doing the operations on those weights. The rule of thumb among numerical analysts using the sparse matrix package is unless your sparsity is 0.1% or less, it is not worth using the sparse matrix package. You're better off with the dense matrix package. We have been able to get actually pretty good results with 50%, but with structured sparsity in Ampere and Hopper and Blackwell. And we're looking at how to do better than that. And there are actually a bunch of ideas on the table, but it turns out this is a particularly sticky, it's easy to get the sparsity, it's hard to actually get good gains from it. Better tiling, so we're basically doing these big matrix computations. We typically break them into submatrix computations, and you can order those loops in different ways. And depending on how you order those loops, you greatly change the amount of data motion and locality in the problem. So every block over there is circuits. There's your reading and writing memories. Real low-hanging fruit. It turns out that we'll write these memories once, and then we'll read them often tens or even hundreds of times. There's a lot of reuse out of these memories. So if you can optimize a memory circuit to be really cheap to read, even if it makes it more expensive to write, that's a good trade. A simple way of doing this is to provide a separate bit line for every cell. It makes the memory a little bit bigger, but it means as soon as you write it, you energize that bit line once. And now the cost to read is just a multiplexer on the output. You're not basically charging and discharging a big bit line. So for a little bit of area and a little bit of write power, you wind up getting way lower read power. And then we're looking at how to basically make the access way cheaper by exploiting the third dimension now that things like hybrid bonding and advanced packaging are around. Can we basically put memory directly on top of the arithmetic units and avoid moving things sideways by moving them a very small distance up and down? So let me talk about a few of these, and mostly I'm going to talk about number representation because that's where we've gotten the most gain in the past. There are a bunch of different ways of representing numbers, right? This is something we teach in our basic undergraduate classes on logic design and computer architecture. Integers are one way of doing it. Floating point is another. Log is one I'm going to go into a little bit more later, where you basically have all exponent. But to make this work, it typically is not a base 2 exponent. It's usually a fractional power of 2, an exponent of 2 to the 1/8 or so. Theoretically, the most efficient way to represent anything is with a code book, right? If I can train a code book to basically put the symbols in the most optimal places on the number line, from a representation point of view, I can't do any better than that. For any given data set I want to represent, if I want to represent it with a minimum mean squared error, there is an optimal code book that will do that. It turns out, though, I got very excited about this. Song and I actually built an accelerator that used code books to do the lookup. The problem is that you then have to do a lookup, and you have to do the lookup into a relatively high precision number format to represent all of those points well, and then do the math at that high precision. So it winds up actually burning a lot of energy, even though from the storage point of view, it is the most efficient way of doing everything. There's a whole field where people like to try to mimic the way biological systems work by representing weights and activations with spiking. This winds up being one of the most costly ways of doing things from an energetic point of view, because what burns energy in CMOS electronics is toggling, right? And to represent a number, you wind up having to toggle a lot. And you can represent things in analog, and that has some advantages until you have to convert back to digital to store or move the numbers. And so what we want to do is for every one of these number representations, we want to ask, what does it cost and what is its accuracy? And so here's a comparison of these on those two things. So what you see is that spiking is really bad on the actually, I don't actually have the energy up here, but it winds up basically matching integer. But rather than, for an integer, if I wanted to say have 8-bit precision, on average, switching from one number to another number, I will flip 4 of the bits, which means it's equivalent to 2 toggles. To represent an 8-bit number on average with spiking, I toggle 128 times. So it's 64 times as expensive energetically as integer to do the same thing. Now, integer has a lot of nice properties, but it has bad worst-case accuracy, and I'll show this in a little while, and that's because your error is the same everywhere. And so if you think about it as proportionally, for small numbers, and it turns out most weights and activations are small, it's a large percentage of the value you're representing. It's 50% at the worst point where you're trying to represent 1.5, and it can either be 1 or 2. At the top end of the range, it winds up being, that's the maximum accuracy and the minimum accuracy here. And it has limited dynamic range. Log winds up being the best for the number of bits. I really should have compared log8 to FP8. But FP is pretty close, and it also has this property that the maximum accuracy and the minimum accuracy are the same because you're scaling your step size as you go. And so the log and the floating point representations are really the way you want to do things. Now, when it comes down to what you're trying to represent, you need to look at what the distributions are. And they're two very different distributions. And so if you prune a neural network, you basically take out the part of the distribution around 0. Typically, the way you do pruning is you train the network, then you find all the weights that are below some threshold, and you force those to 0, and then you retrain the network to have the remainder of the weights adapt to those. And so you've removed the part of the distribution near 0, and you wind up with a bimodal representation like this. Now, if I have an integer representation, I get something like the green x's here, right? Say I have 16 symbols, a 4-bit representation. I'm wasting a bunch of my symbols, 3 on this side and 4 on that side, where almost nothing is happening. Now, I'll explain a little bit later how optimal clipping can handle that. There actually are some numbers out here, which is why they're out here. There's tails to these distributions. But if I train an optimal codebook, I get sort of my 16 points where these dots are, and they wind up sampling the distribution very well in a way that minimizes the error of the representation. Now, if you don't prune, you get something that looks a lot more like a normal distribution, but you still wind up getting outliers. You get things that are, most of the energy here is between 0.5 and minus 0.5, but you get things all the way out to 2, and we'll talk about that in a little bit. Let's see. So let's talk about log representation. For those of us who went to engineering school in a certain era, since only the rich could have calculators, you actually weren't allowed to use them. And so we all did our calculations with slide rules, and slide rules are a way of doing a logarithmic calculation. The scale is logarithmic, and so to multiply two numbers, you add them, and here you'd add them linearly by finding one of the numbers, putting the 1 against that one, and then finding the other number and reading off the effect of multiplying them. And so that's the great thing about log is that they turn adds into multiplies. And log is great. It's got good dynamic range. This is for an 8-bit log representation. And I should explain it means that there's one sign bit here, plus or minus 4 bits of integer exponent, which means 2 to this number, and 3 bits of fractional exponent, right? So this is really 2 to the 1/8 to this number, right? So if you set all these bits to 1, you'd get 2 to the 7/8 out of that part. This winds up being a great way to represent numbers for a bunch of reasons. I can talk about the accuracy and stuff in here. It's better in graphical form. So this is a way of comparing log to integer, right? So with the log representation, here I've taken a 4-bit representation so you can see the steps. It winds up just being tiny little wiggles if I did 8 bits. What you see is when the numbers are small, the wiggles are small. So you have small error for small numbers, big error for big numbers. Across this entire range, the error of a 4-bit log representation is 9%. With integer, you get big errors with small numbers and big errors with big numbers. I should say medium-sized errors, but they're big compared to the small numbers, right? So you're trying to represent 1.5, and you're either going to round that to 1 or 2. Your error is 0.5 out of 1.5. It's 33%, right? And it gets really small up at the top. It's less than 9% at the top. But remember, most of your numbers are small, and that's where these errors are really big. And so integers have problems with that. Now, what's really stood in the way of log representations is the fact that floating point is almost as good. So with a floating point representation, here's a floating point with 2 bits of exponent and 2 bits of mantissa, much like what we have in Blackwell. What you see is you have the same small wiggles at the bottom, but they're a little bit bigger wiggles, so it's 13% error rather than 9%. And then every time you walk those low 2 bits, right, the 2 bits of mantissa, you then bump the exponent. And now you get 4 steps of the next biggest size, 4 steps of the next biggest size. And so it's an approximation that's almost as good as the log and is not quite as foreign to operating. Now with log numbers, multiplies are cheap. You just add 2 log numbers and you get the result of a multiplication. But adds are hard, right? Because what you really have to do is convert to integer, do the add, and then convert back. And that's very expensive. It requires a table lookup. For the integer bits, it's easy, right? That's just a shift. But for those 3 fractional bits here, that's a table lookup in an 8-element table. And the good news is, think about what you're doing in a typical deep learning problem. You're summing, you're calculating the weights of a layer of a network to get one of the activations out to the next layer. Is typically a summation of 10,000 or more multiplications of a weight by an activation. So what you can do is factor out this part to the outside by sorting. There are only 8 possible cases, right? So you do that summation of everybody with an exponent of a fractional exponent of 0. Here's the figure out of the patent. So you take that fractional part, and you basically sort everybody who's got a fraction of 0, you sum together. And then at the very end, you add in this constant that's the table lookup. Similarly, you take everybody with an exponent of 1, everybody with an exponent of 2, and so on. And then you basically sum those 8 things together to get the final answer. So you factored out the expensive part. So you only have to do it once every 10,000 adds, and so the add becomes very cheap as well. Now let me shift gears. So whatever representation you use, whether it's log, whether it's floating point, even if it's integer, even though we've seen that integer has really bad error at small numbers, you want to pick the range correctly, right? So if I have some distribution of weights, say my weights range from minus 0.8 to 0.8, but most of the energy is between minus 0.2 and 0.2, the naive way of doing this, and quite frankly the way we did this for a very long point in time, was to pick the minimum, we picked the maximum absolute value of the weight, and we used that to set the upper and lower bounds of this entire thing. And then we computed a scale factor, and we scaled our numbers so that the dynamic range representable by our number system exactly fit that. Now, when you do this, there is no clipping error, no error that is incurred by taking an outlying weight or activation and clipping it down to the maximum representable value. But there's an enormous amount of quantization noise, right? The other opportunity you have is I could say, look, there aren't very many weights out here. Too bad for them. They're all going to get clipped down to minus 0.2. And therefore, we're going to have some clipping noise by clipping these guys down. But that doesn't happen very often. And as a result of that, our quantization noise gets really small. And so you can pose this as an optimization problem and ask the question, what clipping factor should I pick to get the minimum mean squared error? And it turns out you can solve that problem in closed form. You just have to solve this integral here, and it will give you the factor. That actually winds up being expensive to do, and for weights, that's not a problem. You can do it once. But for activations, you have to do this every time through the network. But it turns out there's an iterative solution that converges very quickly and is very inexpensive to do, which is this approximation down here. And if you do it, what you see for different layers of a network, both the weights and the activations, is shown here. And since this one is just pretty much at arm level, I'll do it. Is if you're doing 4 bits, and you basically do no clipping, you'll wind up being out here, right? You're representing, say, the whole 4 to minus 4, right? And as I scale that down, what I'm doing is I'm basically adding a very small amount of clipping noise in and getting a great reduction in quantization error. So my overall error, the mean squared error on this axis, is going down. And it does it. I've now cut my range in half, and I'm still going down. I get down to the range being cut to about a quarter. Basically, I'm taking 3/4 of my dynamic range and throwing it out, and it's still a win. But then I hit this point where I start clipping a lot, and the clipping noise starts getting to be more than the quantization noise. So I want to stop there. But when I stop there, the way to think about it is, if I had a 5-bit line, it would be about between these two. It's better than 5 bits. It's almost as good as 6 bits to do this. I'm getting more than a bit of extra precision by optimally clipping. So that's trick 1 to let you do with 4-bit floating point what you used to do with 8-bit floating point. The other trick is vector scaling. And the key idea of vector scaling is I'm doing this clipping operation, but on what granularity do I do that clipping operation? Do I clip an entire layer of the network? Do I clip one particular filter of the network? So it turns out that as you pick a smaller and smaller granularity to do that scaling on, you're incurring some overhead, right? Because I have to have a scale factor for that number of bits. But it turns out that if you pick that down to a single vector of like 32 or 64 elements, it's worth those extra bits of scale factor, because now I'm applying that clipping to a much smaller sample set. And therefore, rather than clipping a large set of numbers that have a big dynamic range, I can clip a smaller set of numbers. Here's kind of the cartoon of that. It's not that I'm throwing these out. If that was that much of the normal distribution that I was clipping, my clipping noise would be small. I'm basically saying over a vector of 32, I don't have this big distribution. I have a smaller sub-distribution. I can wind up clipping it more aggressively. And I wind up getting another bit or 2 bits of precision out of doing that. And that's what has let us do the FP4 representation. There's an open compute standard called MXFP6 that's been pushed by Microsoft. And it has a couple flaws with it. Probably the biggest one is it uses an exponent only for the scale factor, where you really want to use a complete floating point number so you can set that scale factor very precisely. But when they came up with the need to have 6 bits, they did that because they weren't doing optimal clipping and they weren't doing vector scaling. Now let me talk about sparsity. This is a figure from the NeurIPS paper that Song Han and I wrote back in 2015. And in this paper, we showed that for a typical multi-layer perceptron, we could lop 90% of the weights out and basically get equal accuracy to what we had before, which really I thought was a pretty great result until we tried to exploit it. And I don't want to tell you how many things we tried that didn't actually get any gain before we got the one that did, which was to do 2-to-1 regular. And the key here is it's structured sparsity. So what we do is we basically take these dense trained weights and then we prune them, but we prune them with a rule that says that we can have no more than 2 non-zeros out of every 4. And with this 2 out of 4 rule then, we can basically take this weight matrix, take only the non-zeros, then we just have a little bit of metadata that says which ones those were, right? Which 2 out of, which 2 choose 4 of them we picked. And then that metadata selects which of the activations match up with that. Then we essentially do a dense multiply and dot product. And so we basically have taken the sparse computation and turned it into a dense computation. I'll just observe this works really well. This gives us a 2x for the matrix multiply parts of the computation. There's a lot of low-hanging fruit that we haven't picked on this one yet. We're only doing 2-to-1. There are some cases where we could probably do 2 out of 8 and still get good results. And we're only doing it with weights. We haven't done anything with the activations yet. And so I think that there's a lot of more room to exploit on the sparsity front here. Now, the way we've prototyped a lot of these ideas is with accelerators. And here's a bunch of the accelerators we've done over the years. Song Han and I did the EIE as a joint project between Stanford and NVIDIA. Joel Emmer at NVIDIA worked with Evelyn Z at MIT and did Iris. And they exploited they experimented with different things. EIE was the first sparse accelerator. And basically what we did is we showed that if we had the actual data for the sparse matrices were in these big memories on the top and bottom, we put the pointers in separate memories so we could walk the pointer structure of the compressed sparse column format without incurring any overhead, because it had its own memories, it had its own logic for doing the computation, and wound up being able to exploit sparsity with extremely low overhead. Iris really sort of was an experiment in what are called data flows, better ways of mapping the computation in space and time. And they came up with these concepts of row stationary and column stationary and output stationary data flows, which showed how to minimize the amount of data movement to get efficiency. SCNN is one of our failed attempts at exploiting sparsity. So the observation that we had, it's great when you're an academic, you have a failed attempt, you write a paper and declare success and move on. But it was a failure, right? And it was a failure because we couldn't commercialize. We couldn't put it into an actual product because it didn't give a gain, right? It was a clever idea. The idea is that for a convolutional network, every weight does see every activation, right? If you have a filter, that filter is going to see every activation. And then it's just a question of where you sum the results. So we basically took every weight and every activation, we fed them into this multiplier array and computed that outer product of every weight times every activation. And we also computed the coordinates of them, because if you took the position of that weight in the 2D convolution filter and the position of the activation that sum of offsets is where that one was going to land in the output. And so we did an operation called scatter add, where we took all those partial results and we scattered them to the proper output activation to sum up. But we did exactly the wrong thing. We moved all the irregularity to the output side where it's most expensive. And the reason it's most expensive there is at this point in time we were doing 8-bit precision operations. So all of these inputs were 8 bits. We were accumulating 24 bits of results. So it's 3 times as expensive to have the irregularity in the output side. So everything we gained by being clever about being regular on the input side, we more than wasted with the irregularity on the output side. And then Simba is really an exercise in scaling where we wanted to show that we could do acceleration on a multi-chip module. And so each of these chips is itself a little AI accelerator with, I think it was a 5x5 array of processing elements. And then we put them in a 6x6 array of chips to get a equivalent 30x30 array of nearly 1,000 processing elements. By the way, each of those processing elements, I think, was a 16x16 array of 16 wide vectors times 16 deep lanes. So if you look at accelerators, why do accelerators accelerate? Well, first of all, they have special data types and operations. As I said earlier, a lot of what we've gained on deep learning accelerators is coming up with better number representations. But in a lot of other, I've also built accelerators for SAT solving and for bioinformatics and things like that. And sometimes you'll come up with a representation that if you tried to implement it on a computer with integer and floating point operations, you would take thousands of operations to do one of what is a relatively simple operation on a native representation, for example, of a gene sequence or of a logical clause. And then the next thing accelerators employ is massive parallelism. Parallelism isn't the 16 cores on a CPU chip. Parallelism here is thousands of things going on in parallel. Optimized memory is probably one of the biggest ones. Memory is expensive, and if you insist on everything going out to some main memory and doing stuff, you're never going to accelerate anything. But if I say, OK, I have a particular memory I need for a particular thing, and I can localize that and put that in the accelerator, I get big gains. And then probably the biggest one here is this overhead. So I showed you before how on a GPU, we had this 20-to-1 overhead of a floating multiply add to the overhead of doing something. For CPUs, the typical overhead is 10,000x, and I will give you a reference for that shortly. And one thing we found over the years doing a lot of accelerator design is that it's a co-design process. And particularly, I did a bioinformatics accelerator with a former student who's now on the faculty at UC San Diego, Yatish Tarakia. And when we took the algorithm and tried to implement the algorithm exactly, the best we could do was about 3x performance improvement. But what we realized is in hardware, dynamic programming was really cheap. And the what's called the seeding computation, which involves a lot of main memory accesses, was exceedingly expensive. So if we rebalanced the algorithm to basically do less seeding, which gave us more false positives out of that stage, and more dynamic programming to reduce those false positives, we could wind up getting a 15,000 times performance improvement. And that's why you really have to understand the algorithms too, because you're not just going to re-implement the same algorithm in hardware. That doesn't work, because these algorithms have been very finely tuned over the years for the cost structure of a typical CPU, where the main memory access doesn't cost that much more than doing a dynamic programming step. So I've been doing fast accelerators since 1985. I built a bunch of simulation accelerators, signal processing and image processing accelerators, and then more recently neural networks. Darwin is the genomics accelerator, and Satin is a SAT solver. So somebody is trying to call me, and that's really annoying. So a lot of people don't understand the magnitude of overhead until they see this figure. This is data from this 2015 paper, which analyzed in great detail an ARM A15 core. And I should say the A15 is a relatively simple core. For a modern Neoverse core, the ratio would be much higher, because this thing is modestly out of order. It's not the aggressive out of order with aggressive branch prediction that a modern core is. But what you see here is if you're doing a simple 16-bit add, that's 32 femtojoules in this 22 nanometer, 28 nanometer process. The overhead is 250 picojoules, right? So we're up, we're up an order of magnitude here and then 3 orders of magnitude there. So it's a 4 order of magnitude gain. And this is why you really need to have complex instructions that do a lot of work to amortize that instruction. It's also why if you have the parallelism, you don't want branch prediction, right? To do branch prediction, you've got to access a couple very expensive memory arrays to look up the prediction parameters before you even fetch the instruction. That makes fetching that instruction many times more expensive. You don't want out-of-order execution, right? That requires maintaining lots of tables to keep everything straight and detecting when you have collisions and all of that. And you have to do memory disambiguation and that sort of stuff. You want an exceedingly simple pipeline. And you ask, why do these modern processors have branch prediction out-of-order execution? Well, it's simple. They're trying to hide memory latency, right? All of this stuff is because when I actually miss the cache and I have to go to main memory, it takes hundreds of cycles, right? And so what I need to do is while I'm waiting for that load to come back, I've got to continue executing. Well, a branch happens about every 5 instructions, right? So I've got to execute through branches. I need branch prediction. I will wind up hitting an instruction that needed the result of that load. So now I have to execute out of order and go beyond that instruction and continue. But there's another really simple way to hide memory latency, and it's called multi-threading. And that's what GPUs do. If I'm executing along and I basically hit a point where I need the result of a load that hasn't resolved yet, I switch to another thread. If you have parallelism with multi-threading is the cheapest way of tolerating memory latency. And that's why the GPU overhead is 20x, and the CPU overhead is 10,000x, or perhaps closer to 50,000x on a complex processor. I'm going to zip ahead a little bit because I think I'm running a little late. I'm going to skip that one. The other thing that you discover very early on when you're trying to build these accelerators is that you have to keep things local. And there's sort of this order of magnitude rule I have that it takes a certain amount of energy to read a local memory array. Say this is an 8K SRAM right next to my arithmetic units. It takes 10 times that much energy to read something globally on chip and 100 times that much energy to go off chip, even to an LP DRAM, which is about the cheapest DRAM around. And so you want to do the bulk of your operations here. So we spend a lot of time in our accelerators architecting a memory system. So we have small little memories sitting right next to our arithmetic units doing things. In our AI accelerators, those are the wait and activation buffers and collectors. So we recently built a series of accelerators. This is one we described in 2019 called Magnet. And Magnet was more than an accelerator. It was actually an exploration. It was a program that would explore the design space of accelerators. It would vary the vector size, the size of these buffers, and find kind of the optimal configuration for that. And actually, one of the things we found is that we needed, I told you about the stuff with Iris that sort of looked at whether we were wait stationary or activation stationary and things like that. We found that we needed to be a hybrid unit, which was basically, wait stationary, partially activation stationary. And we added a level of collectors that are not shown in this diagram to implement that, and that gave us the best performance. More recently, this is the one that was reported in the VLSI Circuits Conference in 2022, and the JSSC papers is 2023, where we used the Magnet design exploration tool, but we were in a more modern technology, and we went to 4-bit precision using the scaling and optimal clipping that I described, so we could do large language models without any loss of accuracy. Basically, what we were able to achieve is just under 100 teraops per watt. And so this is, I think, a nice figure of merit for what is possible. To give you a comparison, I think Blackwell is about 20 teraops per watt. So there's a 5x between what we're not quite shipping yet and what we've been able to demonstrate in the lab. And actually, one node back, this is still in 5 nanometers. Well, some of it might be, right? We always look at what we have here and what's going to go in. So one final thought I want to leave you with on accelerators is that I've always observed every time I build an accelerator, take the bioinformatics accelerator, coding up, I wrote the RTL code for that dynamic programming, and I think I did that in an afternoon. And then it took several months of graduate student work to wrap a memory system around that and an interface to the PCI Express so it could go out and talk to the CPU that was giving it directions and stuff like that. And GPUs are just a wonderful platform on top of which to build accelerators. All of that stuff that takes, actually, it winds up being thousands of person years, of building an on-chip network and building a memory system and building a standard SM to do the parts of the code that don't go in your accelerator can all be done once, right? And now you have your platform. And then if you have a particular algorithm that you want to really accelerate, you can write the code for your algorithm and have a bunch of mapping directives that try to decide how much of that's going to run on the standard processors, where you want custom compute blocks, and do a bunch of what-if scenarios to see what's going to give you the best bang for the buck. And then a tiny bit of, and you should be able to generate this directly from your program code, a tiny bit of logic actually needs to be accelerated. And that can plop into one of these. And with modern 3D packaging technology, that can then just pop right on top. I should say, we did this in Hopper. I was very excited about bioinformatics at that point in time, and I defined the bioinformatics instructions in Hopper. And it just screams on dynamic programming with those instructions. And they're a little bit of logic incorporated right into the standard SM. But for other applications where you may not be able to justify putting it into every GPU chip, you can imagine having some of these you can drop in. And if your acceleration is great enough, these things don't even have to be in a 5 nanometer process. You could take an old 28 nanometer process and turn one of these with very reasonable non-recurring costs and get an accelerator that gives you a 15,000 times speed up. So let me wrap up, since I think I'm a little bit over time. So deep learning was really enabled by hardware, and its progress was limited by hardware. The algorithms and the data have been there for more than a decade at the point in time where GPUs provided enough compute to train a large enough model on enough data in a reasonable amount of time. Since that point in time, you've seen this growth rate since the transformer era, 16x per year in the demand for petaflops to train the largest models. And so we feel a tremendous responsibility to continue providing increased computing performance to stay on that curve. And eventually it's going to flatten out. It will not be sustainable. But we've been doing a pretty good job so far. In what's been come to be known as Huang's Law, we've gotten a 1,000x return in the last decade. Only about 2.5 or 3x of which is coming from process technology. The rest of it is coming from cleverness, number representation, complex instructions, sparsity, and a few other things. On the number representation front, I probably spent the most of this talk on representation. You really want a representation that gives you low error and inexpensive operations, and log numbers are my favorite for doing that. And it has to be inexpensive operations as well, right? We'd be using symbols for everything if we didn't have to do that table lookup and then high precision operations for doing that. Whatever number representation you want to use, you then want to scale it appropriately. And a key thing is you don't want to scale to the maximum minimum numbers. You want to balance your clipping noise with your quantization noise and do optimal clipping. And then there's the question of what is the granularity over which you do that clipping. And what we've found is that it's a small vector, somewhere between 16 and 64. It's not a whole layer of a network. And then I talked a little bit about accelerators. We built a bunch of these test beds to test out the ideas for the next GPUs. And currently we're at about 100 teraops per watt. So there's plenty of room for us to do better than what we're shipping today. So with that, I'd be happy to take questions. I guess I'm supposed to be sitting up here for the Q&A part. Yes. I'm going to take my jacket off because it's hot. Especially right in front of that screen. You're getting roasted by the projector.
OK, great. So I'm Justin Romberg. I'm a professor in electrical and computer engineering. I've been asked to host this discussion section with Bill Daly.
Yeah, I'm going to grab my computer because I actually thought about these questions and wrote down.
Oh, OK, great,
Yeah.
great.
This is what I did on the.
We might change them
over
slightly
here.
in
Okay.
reference to your talk. So we asked for submitted questions for the talk. I assume they were submitted mostly by people sitting in the audience here. They were actually great. So we had it very hard to cut these down to 7 or 8. So I think we have some great discussion points. OK, so maybe I'll start where you were sort of ending up at the end here. So you referenced this Huang's Law, and that, as far as I could tell, one of the submitted questions asked, OK, there's this 2020 article where the columnists kind of put that forth, saying something like, the performance of AI hardware will double every 2 years, and what you showed, it actually
Double every year.
Yeah, double every year. Sorry, double every year, and which you should probably exceeds that a little bit, maybe 3 or 4 if it's 1,000x in the last 10 years. So. You also mentioned that, okay, of course, this kind of exponential increase is unsustainable long term, but can you just give us a feeling for how long you expect NVIDIA to stay on this trajectory? Like, can we see the end of Huang's law, like we've seen the end of Moore's law?
Yeah, so I can't see the end yet. That's a really good way of putting it. So, you know, at NVIDIA, in NVIDIA research, actually, we're not working on the next GPU. Most of that is already pretty well loaded. We're working on the one after that and the one after that. And we already have really good ideas to keep the scaling going, basically for the next 3 generations. And then we have a bunch of, I would call more speculative ideas that are for the generations after that are sort of early stages of investigation. So I don't see, if looking ahead with the best crystal ball that I have, I don't see the end yet. I will say that unlike, the Moore's law scaling of the 90s with CPUs, where every time you made the line width, shorter by square root of 2, you got 4 times as much stuff, or you got, twice as much stuff in the chip because it's an aerial thing, and 2.8 times as much energy efficiency because that was a cubic thing, without it having to do anything, and you just did the same thing over and over again. That scaling doesn't apply here. Every time we get that 2x, it was a different idea. Yeah. And every idea gets harder. So even though I don't see the end yet, the low-hanging fruit's been picked. We're in the middle branches now, and pretty soon we're going to be on those high, skinny branches where it's really hard to pick the fruit.
Sure. But I mean, I guess like a big theme of your talk was algorithmic advances also play a huge role in increasing force, not just hardware. And this is things we've seen in other areas of applied mathematics too, like solving linear systems.
Yeah, and I'll say even there, it's like the low-hanging fruit gets picked first, and it gets harder each time. Yeah.
Okay, good. So there we have another question from our audience that asks, okay, you made reference to a little bit about like Google's TPU or other specialized hardware. So do you see them competing with NVIDIA in the future? And if so, like what role will your kind of software platforms like CUDA play in sort of your competitive advantage in this space?
Yeah, so first of all, they have no fundamental advantage from a cost and performance standpoint. They can't build a matrix multiplier any more efficiently than we can. And once we have MMA instructions, we have amortized out the cost of the general purpose nature of the GPU. I think that they have a bunch of disadvantages. They have the disadvantage of a very limited programming system. We've been developing CUDA since it was launched in 2006. We really started development in 2003. And on top of that, we've built this whole ecosystem of cuDNN, TensorRT, lots of tuning software support for all of the frameworks. And like I illustrated with the MLPerf results, huge gains in performance come from having that very highly tuned software. So while they may say, oh gee, NVIDIA is charging 30% more than they should for their GPUs, so I can have Broadcom, so Broadcom makes those TPU chips, right? And Broadcom's, I don't know if they publicize, but it's pretty widely known that Broadcom's custom chip unit insists on a 30% gross margin, right? So they're getting they're getting those chips for about 30% less than an NVIDIA GPU chip. But for a lot of the key performance measures, the gains from having that really tuned software stack are 2 and 3x. So it's just not worth it from a TCO point of view. And so I think the only reason recently why people have been looking at that is because for a while the supply of GPUs was limited, because of the CoWoS packaging shortage. And I think that's largely behind us now. And so I think it's going to be harder and harder for people to justify trying to build a purpose-built accelerator. They're also way less flexible, and when somebody comes up with the next big model, they're going to be very disadvantaged.
Okay, good. This actually kind of leads into my next series of questions here. So, during the talk, you gave us a very, very nice overview of, what are some immediate vectors for improvement for these things? You've done number representation, sparsity, et cetera. But if we zoom out and just talk about one sentence, what are the real fundamental challenges for AI hardware going forward? If you had to give it 2 sentences on this, what would you?
Coming up with more good ideas. That's probably the biggest challenge. So, I think the easy ideas have been exploited. The number representation was a real easy one, and I think like I said, it keeps getting harder each time. So the last couple real gains to get us from getting really good performance on LLM inference from 8 bits to 4 bits. It took that optimal clipping and it took the per vector scaling. And actually, even then, if you look at the details of the things we tried and which worked and which didn't work, there was a certain amount. It seems always looks obvious in hindsight what you came up with, but you look at all the things you tried along the way that didn't quite work out. it wasn't that obvious. And now, it just gets harder to come up with these ideas each time. I think the next big gains are going to be just more aggressive exploitation of sparsity. We've got 3 or 4 different investigations on the table right now. Looking at that, some of them are starting to look pretty good. I think that we can be much more aggressive with certain of our circuits than we have been. There's a certain conservatism. The people who are responsible for the back end of our design process, these are people who turn out these billion transistor chips. And it's always amazing to me that they work at all, right? Let alone they work the first time, right? We have had A-step success on every GPU that we've taped out since I've been with the company. And to do that is just phenomenal, but it comes from having a incredible level of conservatism. And so I'm always coming up with these crazy circuit ideas that involve really low voltage swings and stuff to minimize energy. And our people who are responsible for this first pass success look at me like I'm nuts. But eventually, we'll start exploiting some of these circuit ideas and reducing energy in that way as well. But really, it's kind of, we need to get a lot of really smart people who understand the problem really well and kind of just think up clever ideas, because that's where these gains are coming from.
Gotcha. Okay, interesting. So that's the clever ideas instead of systematic approach. Okay, so then, I mean, a lot of the things you talked about today are really specialized approaches around, let's say, neural networks for AI, and of course, AI is a however many dollar industry right now. But like, what lessons can we get from NVIDIA's sort of innovations for computer architecture as a whole? Like, is there some influence here on other areas of computer architecture?
Yeah, so I think this is actually probably one of the most exciting times in my many-year career in computer architecture, and it's because now the gains are coming from architecture, and they're coming from architecture, I think, almost entirely with domain-specific accelerators. And I think what NVIDIA has done with deep learning, and to a lesser extent with the bioinformatics stuff in Hopper, can be applied to lots of other problems. And I think that because CPUs are just not getting any faster. They're basically the same speed every generation. And we're not getting any more out of process technology. If you have a problem which is demanding, which takes a lot of time and people are waiting for the answer, you want it to go faster, you want it to be more energy efficient, you really need to look at the algorithms very, very carefully and do an algorithm hardware co-design. And again, just accelerating the algorithm itself is not going to do it for you. Like I said, in bioinformatics, we got like 3-4x from that. We got 15,000x. By refactoring the algorithm to exploit what hardware is good at, not because the existing algorithms have been too specialized for what CPUs are good at. But whether you're doing convex optimization, basically discrete optimization, I'm trying to think of other things, anything that takes a lot of computer time, certain graph analytics, I think that there's real opportunities for acceleration to play a role.
Okay, good. Now, in your talk, we saw this massive 40-foot long thing of servers.
Actually, there's several rows of those.
Several rows of those. And when we think of NVIDIA, that's what we think about. But does NVIDIA have anything to say about like AI on the edge? So on mobile devices?
Yeah. So we make a whole product line. Internally we call it our Tegra product line, but there's the Orin generation and the Thor generation, and they're sort of high-end edge processors. Is the way to think about it. They're sort of the petaflop level edge processors. I'm trying to think of what the specs for Thor are, but they're targeted very much at robotics and autonomous vehicles, where for a lot of edge applications, take your smart thermostat or something like that. It's an I/O device, right? It's going to take all the data it has, it's going to send it up the cloud. You're going to do the AI there, and you're going to send it back down. But in applications where you have to work, even when you may have a partition of the network, or where you cannot tolerate a latency up to the cloud or not. You need to do that processing locally. We do make things that do that, and they include, these chips include our ARM processors, they include our latest GPU, as well as a number of dedicated accelerators. We have what we call our deep learning accelerator, and some vision accelerators as well in there.
Okay, yeah, that's great. Okay, so now we have sort of a different section of questions just in terms of like general advice. So we have many graduate students in the office and undergraduates in the office. So in general, like what advice would you have to new graduates looking for opportunities in high performance computing hardware?
Oh, they should come to NVIDIA. But let me tell them why they should come to NVIDIA. So if I think of what anybody should be looking for in a first job, there are really two key aspects. One is you really want to be, working on a state-of-the-art problem, a state-of-the-art design with the best design tools. And then the other is the people who are around you. You want to have the smartest engineers around you and good mentors so that you get your bachelor's or master's degree, and it's a license to learn. You're not truly dangerous yet. You need to learn a little bit more. And so if you go out into that first job and you get somebody who really inculcates you with the right attitudes about being a great engineer, then I think it'll set you up for the rest of your career. And I can't think of a better place to do that than NVIDIA. We have just wonderful engineers. We also have a people culture where we really value every person, and particularly the new people coming onto the teams, and we enable them. They're listened to, and I think it's a great place to be a junior engineer.
Yeah. I mean, that all sounds like great advice, no matter what you're studying. So, okay, good. And then, all right, so if you're an EC student today, right, and you're looking back on this knowledge you gain and what's important and what's not, what's coming in the modern world, like what courses would you take and what topics would you study, and like what maybe other projects would you pursue if you were to restart college right now?
Yeah, it would be interesting to go back and restart college for a lot of reasons. But I think what's important is to realize that moving into this age of domain-specific accelerators, I think what's really valuable is somebody who's not only sort of a master of electrical engineering, but also has some domain-specific knowledge. And so I would pick some domain that I think would be ripe for acceleration. And I think I probably would not pick deep learning just because that is that quadruped has been beaten to the point you can't even tell it was once a horse. I would, whether it's in bioinformatics or optimization of some kind, pick a domain, become a real expert on it, and then you're in the position where you can do that hardware, software, co-optimization and really come up with something there. And then obviously get a great fundamental background in logic design and computer architecture, and I would include circuit design in there. I find I'm often appalled at how many of our computer designers do not have a really good circuit background.
Okay, that's great. We're taking notes, I hope. Good. Okay, so say you're interviewing a young engineer at NVIDIA. What are you looking for?
It boils down to, I think, probably three major things. One is intelligence, right? You can't fix that if it's not there. The next one is, I think, motivation, which can be fixed to some extent, but somebody with intrinsic motivation, I mean, it just works. I mean, they wind up applying themselves. And then I think it's kind of, attitude. Is it somebody who wants to be part of a team and is got a positive attitude that will bring the whole team up and work together? And part of people skills are part of that as well. I mean, I think very often sort of when people are in college, they tend to work very independently, but everything we do as engineers, often industry, certainly at NVIDIA, we do as part of a team, and you've got to learn to be a team player and basically play your position, support your teammates, and everything the same as if you're on a sports team.
Yeah, communication I think is the almost thing. Work with a team. It's absolutely true. Okay, last question, and this is the kind of out there question we took for our audience. So, how worried is NVIDIA about a quantum computing revolution?
So it's interesting. So a member of our board, who was a partner in a VC firm that invested in a company called Rigotti, came to me, must be like 7 years ago now, and said, "Bill, you should start a quantum research group and start building quantum computers." And I go, "Well, that's an interesting idea." So what I did instead is I started a quantum study group, and I pulled together a bunch of people we wound up having in NVIDIA research who had PhDs in physics and kind of really understood this. And we did a pretty in-depth investigation. This was a number of years ago, but the results still hold true today. And we looked at the state of readiness of the technology and projected its, based on its progress in the past, its progress in the future, which is always a little bit of a risky thing to do because you can't predict the real breakthroughs. But our assessment, we did two other things. So out of this came a bunch of software that's now called cuQuantum, because we realized the one thing that GPUs are really good at is simulating quantum computers. If you want to develop quantum algorithms, you're actually better off doing it on GPUs than you are on actual quantum computers, and that's actually wound up being a very successful product. And then we basically kept the study group alive, and so we basically periodically revisit stuff. And there's been actually some really interesting recent papers on these neutral atom quantum computers, which kind of now starting to displace plasmons as the most promising future technology. But even if you look at them and you look at what people have done with the Josephson junction plasmons, you look at how many qubits they have and the quality of the qubits. And today people are building few hundreds of qubits at a noise level of about 98, 99%. Call that 10 to the minus 2. To get to commercial viability, they need thousands of qubits at a noise level of 10 to the minus fourth. And actually, the noise level is probably the thing that's going to take longer to get to. And so we don't see that happening for at least another 5 or 10 years. And even when that does happen, at first, it's only going to accelerate, in fact, it will ever only accelerate a certain very small niche of algorithms, subparts of overall problems. Quantum computers are fundamentally big compute, small data machines. It's very hard to get bits in and out of a cryostat. Even when they're successful, they will perhaps have a few tens of thousands of logical error-corrected qubits. And so you're not going to do algorithms that require terabits of data on a quantum computer. What you're going to do is you're going to do algorithms that require a small amount of data and lots of compute. And quantum chemistry is a great application for it because you're basically doing what it does naturally. Cryptanalysis of certain, backing out certain one-way functions, like factoring the product of two prime numbers, is another. There aren't that many other things that are well suited to a quantum computer. And even when you do that, if you look at Shor's algorithm for factoring, the quantum part finds the primitive root of unity, but then there's a whole big another part of the algorithm that has to be done classically to actually come up with what those two primes are. And so there's still a huge need for classical computing to complement the quantum computing. By the way, most of the quantum error correction requires a huge amount of classical computing as well.
Good. OK, so not worried, but you'll be ready.
Yeah.
OK, that's great. I don't know where we are on time. 3 minutes. OK.
Take questions
Do you
from
want
the
to take a
audience?
question? Yeah. We have one? Okay.
Feel free to
Yeah, right here in front.
Yeah, just stand up. Yeah.
Hi, I'm Akshat, and I'm a PhD student with Professor Tushar Krishna. So you mentioned about number systems, particularly logarithmic and floating point. I wanted to know what is NVIDIA's stance on posits, posit number format.
Yeah, we've looked at it. We don't see any particular advantage. It's a clever format, having this ability to have sort of an exponent of the exponent. But we have no immediate plans to pursue it. Yeah.
So there has been work from our group as well, where we've looked at a logarithmic posit format, where so logarithmic numbers don't exactly have the adaptability to different distributions as it is. So we use the exponent of the exponent feature which the posits have, and blended that with the logarithmic number system, and we noticed that there's almost no accuracy degradation when we went even down to 4 bits for most DNNs. So.
That's really interesting. I'd be interested in seeing your papers on that. Yeah. So there's one down here. Yeah.
Thank you for the great talk. It's very apparent that the GPUs are unbeatable right now. I'm curious, if there's anything that NVIDIA GPU that cannot do, or not good at?
Well, I mean, it depends on the range of things you're thinking about. It won't cook your dinner for you, but although they get pretty hot.
For example, scientific computing, other physics simulations.
Yeah, so they're really well optimized parallel computers, but we do make a trade-off in each generation about how much die area we want to devote to different things. And so in recent generations, we put more die area into the very low precision MMA operations, and have actually taken it away from double precision. So I think and if we want, if there was actually a large market for people who are doing double precision calculations, we would probably spin a special chip to do that with the area balanced differently. So it's really a question of emphasis. I think the overall architecture is really good for anything that has a lot of parallelism. And the reason why people still buy CPUs is that there's a lot of code out there that doesn't have very much parallelism. Sometimes it's solving a problem that does, and people just haven't parallelized it yet. But I think that if you're running kind of old spaghetti code that doesn't have very much parallelism, you'd rather have a CPU than a GPU. But if you have parallelism, you'd rather have the GPU.
OK, I think we're one more. OK, one more question. OK.
Given that you have made a significant contribution when you were in academia and now at NVIDIA, I wonder what's your perspective on the evolving boundary between academia and industry research? For example, how this boundary has shifted since you began your career, and where do you see heading in the near future?
Well, that's a really great question. Yeah. So the question is on the boundary between the academia and industry. And when I started my career, it was a pretty solid boundary, right? You were on one side or the other. You either chose an industry position or an academic position. And I chose the academic position because I loved teaching. I loved working with students, and I like just pursuing pretty far out ideas that didn't have to have immediate profit justification. I think recently that boundary has blurred a lot, and a bunch of things have happened. And I'm actually quite concerned about one of them, is a lot of people have left the academic world, myself included, for industry, and I think that brain drain is to the detriment of our universities. And another is that there's a lot of people who are now straddling the boundary, and I think that's actually a very positive thing, because it basically causes the professors to be much more aware of what's going on in industry. Their teaching and research become much more relevant to real problems, and then they're also on the industry side. They're bringing in the latest ideas from the university and applying it. And so I think that's a very positive thing. In NVIDIA research right now, we have about 20 people who are joint between NVIDIA and a company. Sonia Fiedler, who runs our Toronto AI lab, is 50% University of Toronto, 50% NVIDIA. Dieter Fox, who runs our Seattle robotics lab, is 50-50 UW and NVIDIA. Gal Chechik, who runs our research group in Tel Aviv, is 50% at Bar-Ilan University, 50% NVIDIA. And I think that's the future model. I think that actually works really well. I know that a bunch of universities, Stanford kind of kicked me out because they don't. I would have been very happy to be 50-50. They don't want that. They have what's called a conflict of commitment rule, where you have to be 100% time at Stanford and no more than 1 day a week consulting outside. I think that's kind of a dated philosophy these days. I think it actually gets in Stanford's way.
It's good.
Yeah.
Very interesting. Okay, big round of applause. Thank you.